Great, thanks, Sheila, and good afternoon, everyone. I have the pleasure of rounding us out for this afternoon to overview the Concentrating Solar Thermal Power program here in SETO. I'm Avi Schultz. I'm program manager for CSP. And if you can go to the next slide, please. Shown here is the team that I work with, who do, of course, all the hard work to actually execute our strategy and program. You're going to be hearing over the next 45 minutes from all of the technical staff on our team, technology managers and advisors, and the fellow who's working with us. And I'll introduce all of them as they come on. But before I do that, of course, also want to thank the folks you won't be hearing from, Christine Bing, Patty Clark, and Tiffany Jones, who help with a lot of the details of the project management aspects of our portfolio. So want to thank them, and then I'll introduce everyone else as we go ahead. Next slide, please. So as Garrett talked about at the beginning of the day, we have a goal on the CSP team of getting by 2030 to 5 cents per kilowatt hour electric for CSP that we think of as kind of a base load type configuration with at least 12 hours of thermal energy storage. Of course, the main value proposition for CSP is that it is solar energy that is dispatchable on demand through the incorporation of thermal energy storage. That represents about a 50% decrease from where we see the baseline cost today at about 9.5 cents. And just shown on this slide is one potential roadmap that we're focusing our strategy on to get down from that 9.5 cents to 5 cents. If you click, please, you see that a significant portion of this strategy is really focused on developing high efficiency power cycles that rely on significantly higher operating temperatures than current CSP technology. And we target about 700 degrees Celsius as an inlet temperature for achieving the efficiencies that we think are required. Next click, please. In addition to CSP for electricity, more recently, our program has begun to focus on non-electricity applications for concentrating solar thermal, in particular, looking at using solar thermal technologies to address decarbonization in the industrial sector, which of course is heavily reliant on currently fossil fuel-based sources of thermal energy. Next click, please. Of course, those industrial processes, as I just mentioned, are heated through combustion of fossil fuels. So if you click one more time, what we're really aiming to do in our program is replace fossil fuel combustion with concentrated solar energy, either by directly heating industrial processes on sun, or of course, utilizing thermal energy storage to capture that solar energy and exchange it with fluids or processes to deliver that heat when needed to industrial processes. Click one more time. And we have a general goal in this part of our program to reduce the levelized cost of heat, the way we think about this, with thermal energy storage to approximately 2 cents per kilowatt hour thermal. That would make it approximately competitive with natural gas combustion across a wide range of temperatures relevant in different industrial processes. And you'll hear a little bit more about both these strategies throughout the talk. Next slide, please. Like the other programs in SETO, we of course primarily achieve our objectives through solicitations, both funding opportunity announcements, as well as lab calls to the national laboratories, in addition to a couple of prizes that you'll hear about in a little bit. Just shown on this slide is a little bit of a snapshot of the programs that we've announced and have launched in recent years that represent the projects that are currently active in our portfolio. I just want to really point out that this is, that you heard a long time ago, earlier in the day before our lunch break, about what we're doing in our office to achieve the JEDI goals that we've set out for ourselves. And this process is really where those goals, where we've really been putting, the rubber on the road in terms of implementing diversity plans in the most recent FOAs, implementing diverse reviewer pools, and really doing the best we can to bring a wide variety of applicants to these programs. Next click, please. Through these programs, you can see what our current portfolio looks like, just shown here both by funding and by number of projects. And what you'll immediately notice is that just kind of by the way we're splitting up these topic areas, a significant, almost half of our funding in the CSP program is going to what we call CSP systems. And included in that, the reason that we're calling them CSP systems is we have a number of pilot and demonstration programs that are relatively large dollar amounts that really represent first of a kind demonstrations of fully integrated or partially integrated solar thermal systems at a relatively large scale, megawatt or more in a couple of cases, where we're really trying to demonstrate novel technologies. And you see, if you look by number of projects rather than by funding, you see the distribution. It's significantly smaller portion of our portfolio number of projects. Next slide, please. Before we dive into the rest of the portfolio, I wanted to say a word about current deployment of CSP. So shown on this plot is a timeline of deployment globally of commercial CSP technology. There's about 7 gigawatts, maybe slightly over 7 gigawatts deployed globally now at this point, both in the US as well as recently, more recently in many other parts of the world as well. At this point, so a lot of this has just happened in the last 5 to 10 years. And what this has really enabled us to do is now we have essentially an existing real world laboratory where we can gain significant knowledge and data about the actual operability and reliability and the best practices of commercial CSP technology. If you click once more on this slide, a couple of years ago, we commissioned a report from NREL to really actually talk to all of these commercial plants and all the operators and really learn the best practices, collect the best practices and lessons learned from this global fleet, and really identify what remaining work needs to be done to optimize the reliability of this technology. And if you go to the next slide, the result of that was a funding topic that we released last year. And we just recently announced a number of awards addressing the highest priority reliability issues in commercial CSP technology. I wanted to really highlight these because these projects were just announced a few months ago. They haven't actually begun yet, so they're not formally part of our peer review process this week. But I did want to point out what we're working on addressing. And I really want to point out that second group in this table focused on nitrate salt tanks, where we have a number of projects really working to identify and standardize best practices for reliable thermal energy storage, which of course is the key component for the value of CSP technology. Go to the next slide. I now want to hand this off to the technology managers on the team, and I'll start off with Andrew Prescott to talk about our work on solar collectors. Andrew?
Thanks, Avi. The next 2 slides, I'm going to talk briefly about our collector efforts and the CSP team. This slide shows our historical past and also our current efforts. Historically, we have funded a lot of projects, collection projects to support CSP, specifically R&D projects. We could simplify the billing of these into 2 major categories, if you think about it this way. One is the solar field capital cost reductions, and the other is improved metrology and characterization. This is simplification, but I think if you look at the first bin, I think that could be further broken down into low-cost material replacements and simplified heliostats and truck designs, but also other collector designs like linear Fresnel for faster assembly and field deployment. I'll give one example here. It's a green parabolic truck collector that we have funded in the past funding opportunity called Collect, where they tried to look at the different simplifying the topology and using a special grade of wood for the structural material to try to reduce the cost and simplify the number of components in the truck for the collector. In the second bin, we could actually talk about some of the efforts. One is accelerating field calibration for improved energy output, and also minimizing operating costs through things like automated solar field analysis and control. I give 2 examples here. One is an effort, a joint effort between NREL and Sandia, looking at using UAVs to characterize the optical errors in the plant, in this specific case, heliostat plant. Another effort is an effort by NREL, looking at trying to further understand the fundamental physics drivers for understanding wind loading in heliostats, and how these CSP support structures and collectors, how they see the wind loading, and characterizing that and be able to predict that in deep array installations. Of course, it's just a small subset of our portfolio, but I think this gives a good example of what we're trying to fund and continue to fund. Next slide. Now, in addition to these projects, we realized that there was a gap. There's a gap in terms of understanding of the R&D for heliostats in particular. And so we, DOE CSP, decided to solicit and fund a large effort to better understand heliostat R&D and try to identify gaps that we can take a look at and try to prioritize, and also try to find solutions to part of the development of CSP collectors heliostats. And so this effort, we funded an effort by, it's jointly led by NREL and Sandia, but they are also partnered with the Australian Solar Thermal Research Institute, or ASTRI. This consortium is actually called Heliocon. It's a 5-year, $25 million collaboration among the 3 entities. Some of the key goals of this consortium is accelerating innovation in heliostat development and reliability, developing national lab core capabilities and infrastructure, and also encouraging collaboration between the CSP industry and US researchers. The consortium is currently working on developing an extensive road mapping document to identify these gaps and prioritize these needed initiatives for furthering the development of the heliostat technology. After this roadmap is completed, the goal is to issue periodic RFPs, requests for proposals, and this will help to foster the collaboration between Heliocon, industry, and academic institutions. One of the benefits of this consortium also is that we have an additional goal to further develop and diversify the research and commercial workforce for CSP. And so this is a very large effort that we are looking forward to seeing success over the next few years. And with this, I will move on to the next slide for one of my other colleagues.
Great. Thanks, Andrew. Our next speaker is Dr. Rajgopal Vijay Kumar, or Vijay, to talk about our power cycles portfolio. Vijay?
Can we switch screens?
No, Vijay, we'll just
okay, I'll go ahead. I'll go ahead. So my topic is going to be about the advanced thermal power cycles, particularly supercritical CO2 cycles that focused or that is focused on reducing the cost of the power block and the balance of plant, and also to improve the efficiency of the power cycle. Next slide, click through. The programmatic object on this area is to develop and demo supercritical CO2 power blocks that target greater than 50% efficiency and development of turbomachinery, recuperators, air cooling capability, and primary heat exchangers. This is all oriented towards attaining a high efficiency SCO2 cycle that is coupled with existing thermal energy storage or advanced thermal energy storage receivers and heliostat fields. The primary goal here is to reduce the cost and increase the efficiency of the turbomachinery system that has been validated at megawatt electricity scale at while developed at various companies in US and the world, and has been tested and validated at SWRI. In parallel, because of the higher temperature targets, the work has been also has been supporting R&D on materials and manufacturing for reducing the cost of the CO2 power block to below $900 per kilowatt electric, and with turbine inlet temperatures greater than 700 degrees centigrade. In the more immediate time period, the intent has been to integrate the CO2 power block with thermal energy storage and demount at actual power plant site at approximately 600 degrees centigrade turbine inlet temperature. Next slide. So what have we done so far with the SEO2 power cycles? We have tested an expander developed by General Electric at Southwest Research Institute that has been tested at 1 megawatt electric 715 degrees centigrade for 7 hours in an SEO2 loop built at Southwest. We have tested a compressor and an expander integrated together, developed by Hanwha Power Systems at Southwest Research has been tested to again at the same loop to 1 megawatt electric to 715 degrees centigrade, compressor inlet temperature a few degrees centigrade above the critical point. Finally, General Electric and Southwest Research have tested a SEO2 compressor with up to an inlet temperature of 35 degrees centigrade. Based upon all the successful work that has been done here, the program has continued to work on the remaining shortcomings that include the seals that is being tested at developed by Eagle Bergman and tested at 550 to 700 degrees centigrade dry gas seals. We are working on bearings with General Electric and with other private companies. Finally, we are working on air coolers development by Vacuum Process Engineering and Southwest Research with the intent of testing a megawatt thermal sized air cooler. So after going through the research topics that are shown here, what is left outstanding is the remaining R&D challenges are low-cost manufacturing and fabrication for turbine casing, recuperators, valves, air coolers, all of which are undergoing research and development right now, and improved performance of seals and bearings to meet high efficiency targets for various temperatures. Next slide. In parallel, the other half of the power cycle work is the need to integrate integrate the power block with the thermal energy storage. And a lot of our research work has been focused on integrating particles with high temperature particles heated by the receiver with a CO2 power block. The work that is ongoing under DOE funding is in steps starting at 20 to 100 kilowatt thermal developed by Solex and BPE and tested at Sandia at various temperatures at various temperatures and various materials to attain heat transfer coefficients. In parallel, we are also working on new research areas that involve development of fluidized bed heat exchangers, moving bed heat exchangers at Sandia to reduce some of the difficulties in attaining high cost, the cost targets of $300 per kilowatt electric using high nickel alloys. We have looked at silicon carbide and fluidized bed heat exchangers to attain the heat transfer performance and cost goals. Finally, all of this is coming together at a 14 megawatt thermal moving bed heat exchanger that is being procured by Heliogen for a test facility in California that is being manufactured by Solex in collaboration with VPE. So with these research areas, the remaining R&D challenge is the nickel alloy heat exchangers grossly exceed the $300 per kilowatt electric goals. The goal is both the 200 to 400 watts per meter square at large scale goals have not been met as of today, although it has been met at 20 to 50 kilowatt, 20 kilowatt scale. There is no functional molten salt SO2 heat exchanger that is available at 700 degrees centigrade because the research has not progressed to a level to build a loop and test the heat exchanger. Next slide. Finally, the completion of a number of these research areas have come together to develop and test a first of a kind SEO2 test facility integrated with thermal energy storage, receivers, and solar field with heat input from the solar field in California by a private company who has an intention to develop this research work into a commercial use by an Australian investor. It's a 5 megawatt electric SEO2 cycle at 600 degrees centigrade turbine inlet to enable low temperature alloys. Heat input is from a number of heliostats, 25 megawatt thermal or so, through 3 receivers of each of 13 megawatt each, and finally transferred to the power block through 8-hour 213 megawatt thermal solid particle thermal energy storage, which is integrated to the power block through a heat exchanger. The testing capability for this test facility involves an RCBC operation, the test of proof of RCBC control and integration with thermal energy storage, running the turbo machinery for a number of hours and proof that its durability and its operation, and a first of a kind thermal energy storage and heat exchanger that has been tested at multi-megawatt scale. Next slide. I think that concludes the research area, and I transfer it over to Shane.
Yeah, thanks, Vijay. So Vijay just gave us a nice overview of all of our work on advanced supercritical CO2 power cycles. Next, we're going to hear from Shane Powers, another one of our technology managers, who's going to talk about the solar thermal side of this, how we're developing technologies to deliver solar thermal energy at 700 degrees C or above. Shane, you go
ahead. In May 2019, the DOE announced a $63 million competitive solicitation aimed at the development of concentrated
Shane, sorry, Shane, your audio is a little coming through a little garbled.
Okay.
Shane, can you try calling in on your phone?
Sure. Take a minute.
Let's give Shane just 1 minute to see if he can correct his audio.
I'm sorry. I'll get on the order.
Okay, no problem, Shane. I'll go ahead and walk through your slides. Having a lot of trouble hearing you. Sorry about that technical mix-up, everyone. So this, in order to develop technologies to deliver the high temperature solar thermal energy that we need, we developed a program that we call Gen 3 CSP to indicate the advanced, the next generation CSP technologies we were developing, and we competed 3 different pathways that we were looking at, focused on using particles, solid particles, advanced liquids, or gas, or other fluids as the heat transfer fluid to transport the high temperature heat. In March, we actually announced the down selection within that program to just one single path. And we announced that Sandia National Laboratories, who've been leading the solid particle system, would receive $25 million to construct a megawatt scale test facility at the National Solar Thermal Test Facility at Sandia in Albuquerque, New Mexico. And that project, that demonstration is just getting off the ground, and they're in the process of initiating procurement to begin construction of that. If you go to the next slide. You can see a little bit of the context of how we ended up making that decision, based on the substantial work that all 3 teams did to really do detailed system designs of their competing pathways. We then had those designs reviewed by an independent merit review committee, and ended up selecting the solid particle pathway for a few different reasons. The real significant strengths we saw of using solid particles as heat transfer media is the system simplicity for construction, operation, and reliability. So relatively little in terms of chemical compatibility or material controls or system controls that would be needed for the solid particles as opposed to the fluid-based pathways. Solid particles have an extremely wide operating range and even an opportunity for further temperature increases, as well as the applicability of solid particles potentially to other solar thermal applications. So for example, using catalytically active particles is one potential concept that's being explored in a number of projects. However, there are a number of gaps that still remain for the solid particle system that we're going to be working on with Sandia, as well as with a number of our other awardees in this space, including a need for real optimization and validation at scale of the receiver for a particle system. The cost of the particles has been shown to be a significant sensitivity in the levelized cost of energy of the entire system, as well as demonstrations at scale of the flow control and particle handling of these systems, which is, again, needs to be demonstrated at commercially relevant scale. Next slide, please. However, there are, there was a lot of really great work I really want to emphasize that happened in the liquid and gas pathways led by National Renewable Energy Laboratory and Brayton Energy, and there may, in fact, still be a significant opportunity for continued work in those pathways and applicability for those heat transfer, high temperature heat transfer media for other applications. There are, however, a number of gaps that still need to be retired in terms of R&D, in particular for the liquid pathway. They're really focused on using chloride salts as a low-cost thermal energy storage media. And there's significant work that we're still undergoing with NREL to validate the thermal storage tank designs and corrosion detection and controls subsystems for chloride salts. In addition, there are interesting synergies with using sodium receivers, so receivers that use sodium as the heat transfer fluid just in the receiver, but then integrating that in the near term with nitrate salt TES, that's the existing thermal storage media used by the commercial CSP industry, that may create a on-ramp for chlorides in the future. In addition, the gas pathway still needs more testing to validate reliability of receivers for high flux applications. So in particular, that was one of the challenges for both the liquid and the gas pathway, was really being able to show the reliability of tubular receivers under the high flux conditions that are needed for these high temperature applications. However, the gas pathway, again, led by Brayton, did a lot of really fantastic work designing particle thermal energy storage, however, using a gas receiver, but using particles, again, as their thermal storage media, and did a lot of good work at showing that particle to gas heat exchangers could have significant benefit for a wide variety of future applications. However, a significant challenge for the gas system is developing system designs that can get to high efficiency by minimizing pressure drop. Pressure drop really identified one of the key challenges for a gas heat transfer fluid. Next slide, please. And now I'm happy to turn it over to Matthew Bauer, another one of our technology managers, to talk about our high temperature components work that is really supporting a lot of the applications, both Gen 3 and industrial processes. Matt?
Thanks, Avi. In the following 3 slides, I'm going to provide some context for the CSP program's high temperature component and characterization track. Solar receivers are, of course, just a unique heat exchanger which convert concentrated sunlight into usable thermal energy. And similarly, a solar reactor converts light into an endothermic chemical reaction. The solar receiver reactor often must handle the most extreme conditions in a solar thermal system, particularly extreme thermal stresses, making them a concept limiting component. SETO's programmatic goal is to develop novel receivers and reactors, which may enable new systems by allowing for new heat transfer media, higher temperature operation, or unique solar thermal chemistry. To do this, we look holistically at all the criteria a novel system is satisfied to become a commercially viable system. Looking at the fishbone diagram on this slide, it indicates that it's inadequate to just home in on research for a single innovation. And we programmatically seek research teams who can holistically de-risk receiver concepts. So the areas of active research under receivers and reactors include particle-based receivers for a range of applications, including Gen 3, solar fuels or general transportable energy production, ammonia synthesis and other commodity chemical production, receivers which enable 700-degree-Celsius power cycles, higher temperature materials, lifetime modeling tools, and megawatt thermal testing campaigns. Next slide, please. Shifting gears slightly, thermal energy storage is the heart of a CSP system. Without it, the value proposition would be greatly reduced. Even though many of the earliest commercial TS products were CSP plants, thermal energy storage is much bigger than CSP, and we have to think bigger to develop the most market viable system. Could you click one more time, please? Shown here are a range of the inputs on the left and the outputs on the right, which we can think of, which may take advantage of a thermal energy storage subsystem. Can you click to the next animation, please? Traditionally, SETO is focused on sensible thermal energy storage for dispatchable power production. On the left is the Crescent Dunes 1 gigawatt hour hot storage tank, entire gigawatt hour of energy stored in that vessel. And on the right is the conceptual particle thermal energy storage for Sandia's Gen 3 particle pilot plant. So these are kind of the conventional CSP in to dispatchable power out form. Next animation, please. It may also be commercially viable to develop grid charged thermal energy storage systems. Here, through either resistive heating or heat pump, the hot storage is charged by the grid for later dispatch. This may give the opportunity to more rapidly de-risk and expand the supply chain for viable concentrating solar power thermal energy storage systems. Next animation, please. Or you could think of increasing the complexity of the system and value by hybridizing a pumped thermal energy storage system with a CSP solar input. There are a variety of thermodynamically advantageous ways to do this, where the system could be superior to the sum of its parts. Next animation, please. Real quickly, I'll note the evolving electricity demand profile increases the demand for dispatchability from all electricity producing technologies. Here's a schematic of TerraPower's nuclear energy concept, including solar salt as their thermal energy storage medium. Next animation, please. As Garrett and Avi have both indicated, we're increasingly focused on thermal energy storage to decarbonize the industrial process heat sector. This can be done with both grid electricity or concentrated solar energy as the input to create thermal products appropriate for the application temperature. Next animation, please. One such application you can think of and that our office is focused on is the low temperature clean water through solar thermal desalination. Shown here is a traditional CSP plant coupled to a multi-effect distillation desalination plant. We can think of this kind of process intensification or value proposition stacking as a way to get more out of our thermal energy storage vessels and have a broad value opportunity. Next animation, please. A more extreme example of stacking value has been proposed by Arizona State University in a 3-level thermal energy storage concept. Here, a standard CSP power plant concept with daily thermal energy storage is coupled with a weekly thermal-chemical energy storage loop. And finally, by using a mix of thermal energy and grid electricity, hydrogen could be produced for seasonal thermal-chemical energy storage or to sell directly. And in the last example I'll give, Michigan State University has developed a concept to directly irradiate a pelletized media to endothermically produce a sulfur-based fuel at a CSP plant. This fuel could be discharged locally or shipped to another power plant or a completely different energy application to take advantage of thermal-chemical energy. And last animation, please. These are just like a small subset of the examples that illustrate the different ways one could put a system together that takes advantage of thermal energy storage. The CSP programmatic goal is to best leverage these inputs and outputs to develop a solar thermal systems which contribute to decarbonization. Next slide, please. The last slide I'm going to cover in this track is on characterization side of our high temperature work. Here, I'll provide a summary and examples of the different forms of characterization, validation, and monitoring, which we strategically focus on. And I've broadly bin this into 4 areas. First animation, please. The most fundamental of these is basic media property identification in highly controlled environments. For an example, I'm highlighting a seedling project at the University of Dayton, focusing on identifying particle flow behavior at high temperatures. Key challenges include describing a reproducible environment and generating data in a manner that is broadly exchangeable to folks who need it and created in a fashion where they don't need to recreate their own custom experience for every change in the flow profile they're interested in. Next animation, please. Across just about every novel CSP concept, our immediate question is, will the innovation work for the lifetime of the power plant? Or is it cost effective to have a replacement strategy? It's critical that we have sophisticated methods to prove lifetime performance of components and to ensure that components survive for 30 years. Shown here is the National Solar Thermal Test Facility at Sandia, where they use the ASHES facility to rapidly produce flux swings in solar absorbing materials at a speed which a cloud could cross over a solar field. so we can see what the effect of a rapid change in a receiver surface temperature. A programmatic goal is to develop standard methodologies to account for such accelerated lifetime determination for a variety of components. Next animation, please. Advancing to more applied measurements in operation, characterization of local properties can be critical in illuminating the performance of a developing component. For example, in studying an original particle heat exchanger, one could create models to predict the inlet and outlet temperatures, but still be dumbfounded as to why the actual experiment didn't match with the original models of temperature in and temperature out. Shown here is an example of a local thermal flux measurement developed by UCSD, where an oscillating laser and lock-in amplifier are used to measure a local and about millimeter scale temperature decay to determine heat transfer rates at an interface or just across a particle layer boundary. And lastly here, tools for monitoring the operation and performance of a plant are hugely important. The example that I'll provide was developed by NREL to monitor hydrogen permeation into the vacuum tube of a trough solar receiver system and develop a maintenance strategy for removing that vacuum to maintain highly efficient receivers and maximize the power produced by the plant. Click one more time, please. Across these examples and much of our portfolio, the thematic challenges which make characterization development unique for CSP include handling harsh environments, developing nuanced information to better understand novel components, data reproducibility for others to build on, specifically findable, accessible, interoperable, and reliable, reproducibility of the actual environment of interest, and lastly, long-term or endurance and performance testing. Thanks for your time and attention, and I'll yield the floor back to Avi.
Thanks, Matt. Now just to close out the section on high temperature components, I'm happy to introduce Kamala Raghavan, the newest technology manager on our team, who's going to talk a little bit about our strategy on novel materials development. Kamala?
Thank you, Avi. So from the presentation so far, it's very evident that CSP service conditions are harsh, which simply means a lot of material research. And also over the course of the presentation, there was mention to material research at several places. So here I will give a very broad overview of materials portfolio in our office. Essentially, we have a two-pronged approach to addressing the material challenges. One is to do continuous improvement to the known materials that have proven harsh environment performance. For example, say nickel superalloys. And the other is to invest in novel material systems. So if we look at the funding chart here, nickel alloys contribute a big percentage of our funding, followed by another proven high temperature ceramic material, which is silicon carbide and composites. Along with these, we have also funded cermets, max phase materials, graded materials, etc. Steels also constitute a good percentage of our funding portfolio. These are very true for components with lower temperature requirements. And very recently, we have funded oxide dispersion strengthened alloys as well for higher temperature steels. As per the fabrication techniques themselves, we have funded both traditional and advanced manufacturing methods. Some of the efforts are primarily to address cost reductions, and the others to improve the performance and properties of materials. We also have funded innovation in welding and joining technologies, and these are extremely important for scale-up and system integration. And not to mention, and actually, like it's very important that all these material efforts are strategized to progress to higher TRL and MRL. So with this quick overview on materials, I pass the baton back to Avi. Avi, please. Thanks.
Great. Thank you, Kamala. Next slide, please. Just in this last section, or almost last section of our presentation, we wanted to come back to our strategy on industrial decarbonization and industrial process heat. As I mentioned at the beginning of this presentation, we've recently been doing a lot of thinking about how we can develop solar thermal technologies to replace fossil fuels to provide reliable, low-cost heat for industrial processing. Next click, please. Our strategy here really kind of focuses on three different thrusts. The first is reducing the levelized cost of heat. Of course, with thermal energy storage that's delivered to the industrial processes. And a lot of that work overlaps heavily, of course, with our solar collectors portfolio. The vast majority of that cost of the levelized cost of heat is the capital cost of the solar collector technologies itself, either parabolic troughs or linear Fresnel for lower temperatures, or heliostats and towers for higher temperature applications. And again, we're really targeting roughly about 2 cents per kilowatt hour thermal at any of those temperatures. So again, that's just something to point out there, that at the lower temperatures, it's sometimes a little bit easier to hit that target. At significantly higher temperatures, costs become more challenging. That's part of what we're thinking about in the heliostat consortium that Andrew talked about before. The second focus of this strategy is improving the thermal efficiency of solar thermal coupled processes. Of course, the name of the game with solar technologies is improving efficiency. So therefore you can reduce the capital cost that is required as much as possible, given that, of course, the vast majority of the cost for solar systems is capital cost. So for example, you'll hear in a minute from about our solar desal prize, where a significant amount of that work has been in improving the efficiency and developing higher efficiency thermal desalination technologies. The final part of our strategy in industrial process heat is solar fuels, essentially. So of course, there is going to be both a geographic and temporal limitation in terms of how you directly apply concentrated solar thermal energy to industrial processes. If we can use that solar thermal energy to generate energy dense, easily transportable fuels, then you can significantly expand the potential market for essentially the application of solar thermal energy to industry. And you'll hear a little bit about that in a minute. So with that overview, I'm going to turn it over to the next slide to Shane Powers, who I believe has his audio working now, and you'll all be able to hear from him. Shane?
Thank you, Avi. Can you hear me?
Yes, we can hear you great now.
All right, great. All right. In 2020, SETO launched the American Made Challenges Solar Desalination Prize Contest. This contest was initially launched as a $10 million competition designed to accelerate the commercial development of thermal desalination systems powered by low-cost solar thermal energy. In 2021, due to the popularity of the contest, SETO launched a second round, adding $5 million to the prize pool. The goal of the prize is to expand the availability of fresh water by cost-effectively treating saline water using solar energy. Current competing technologies, particularly RO, rely too heavily on grid availability and often cannot handle the high salinities of industrial and agricultural wastewater, water from oil and gas produced water, or concentrated brines, perhaps associated with ZLD systems. So the prize is conducted through 4 rounds, beginning with a simple, innovative idea and culminating with the construction of a pilot scale facility. Currently, round 1 is in the 3rd contest with 8 competitors remaining, and round 2 is in the 2nd contest, the teaming contest, with 12 competitors remaining. The grand prize is $1 million, and each team wins increasing amounts with more competition throughout the 4 contests. And for more information, you can visit the HeroX Solar Desalination Prize online. Thank you.
Great, thanks, Shane. Next, we're going to move on to our solar fuel strategy, and I'm happy to introduce Joe Melville, who is the newest member of our team. He's a Science and Technology Policy Fellow who's been with us just a few months and has already made a great impact. Joe, you ready to go ahead?
Thanks, Avi. I'll keep this quick. An emerging area of work in the CSP team is the development of new methodologies for solar to fuels conversion, especially as it relates to energy storage, transport, and delivery. Foundational to any solar to fuels work is the generation of clean hydrogen. Next. The CSP team is funding work in high temperature steam electrolysis using integrated CSP and PV systems. We're funding this type of research at Sandia National Laboratories. Next. And we also have a similar CSP PV to hydrogen thrust at NREL. Next. Also of interest is the synthesis of zero carbon fuels like ammonia. Next. The CSP team is funding work at Sandia for the solar thermochemical production of ammonia. Next. And we're also funding similar work at Texas Tech University on the application of ammonia formation and dissociation for thermochemical energy storage. Next. Finally, solar to hydrocarbon fuels are of interest due to their potential compatibility with legacy infrastructure. Next. CSP projects in this area include work at Arizona State University on high temperature solid oxide CO2 splitting using non-stoichiometric Syria. Next. As well as integrated receiver reactor designs for solar syngas for Fischer-Tropsch routes to hydrocarbon fuels. Next.
Great, thank you very much, Joe. To round out this presentation, we wanted to just say a few words, not about our technical strategy, but about the thinking that our teams put into our funding modality and the way in which we structure and request projects to come into our solicitations. So I'm going to bring Matt Bauer back briefly to talk a little bit about some of the strategies we've implemented there. Matt?
Thanks, Avi. This is a topic very near to my heart of figuring out how to best utilize the funds strategically to maximize impact. One funding modality I'll highlight is SIPS, which stands for Small Innovative Projects in Solar. It's our effort to develop a streamlined seedling project pipeline along with the PV program. This program solicits $400,000 projects for 18 months periods. The SIPS projects featured reduced application steps, reduced documentation requirements, and a decreased review timeline. Since 2018, we funded approximately 30 SIPS projects, and we think this program has been successful by increasing the size of our R&D community significantly, perhaps doubling our count of principal investigators. And of course, increasing the diversity of institutions and researchers involved in CSP research. The effects of the research have been strategically important as well, as we've had the risk tolerance to investigate some unique high-risk CSP frameworks. Next animation, please. Shifting gears, our solar tiers framework was piloted last year in a receivers and reactors topic. The acronym stands for Scalable Outputs for Leveraging Advanced Research. And as this pyramid indicates, the tiered approach attempts to leverage R&D at a variety of technology maturity levels. However, all work must focus on developing knowledge that can advance to a pilot scale demonstration and beyond. Even tier 1 type material discovery projects would be pressed to consider the eventuality of a 10 megawatt system. And we hope that this framework creates a natural opportunity for ideas to advance implementation. Once again, thank you for everyone's time and listening today. And with that, I believe this concludes the CSP program's discussion. I'll yield the floor back to Sheila.